Welcome, everyone. Thank you for joining us for our UC Davis College of Engineering Distinguished Lecture. I'm Jennifer Curtis, Dean of the College of Engineering at UC Davis. Before we begin, I wanted to share a few housekeeping items. This lecture is going to be recorded and is going to be shared on our college's YouTube page after the event. Please submit questions using the Q&A button, and those questions will be discussed during the Q&A session at the end of Dr. Goldwasser's lecture. Thank you very much. In our College of Engineering, in our Distinguished Lecture Series, we host international experts to share and engage with our college community. We are so very pleased that our distinguished lecturer this year is Dr. Goldwasser, who is the director of the Simons Institute for the Theory of Computing and a professor of computer science at UC Berkeley. She is also the RSA Professor of Electrical Engineering and Computer Science at MIT, and a Professor of Computer Science and Applied Mathematics at the Weizmann Institute of Science in Israel. Dr. Goldwasser received a BS in Applied Mathematics from Carnegie Mellon University and an MS and PhD in Computer Science from UC Berkeley. Among her many accolades, Dr. Goldwasser is the recipient of the ACM Turing Award. She is also a member of the American Academy of Arts and Sciences, the Association for Computing Machinery, the National Academy of Engineering, the National Academy of Science, the Israeli Academy of Science, the London Mathematical Society, and the Russian Academy of Science. We are very honored to host you. Please welcome Dr. Goldwasser.
Thank you very much. And thanks for the invitation, and that finally we can actually do it in a manner of speaking. So what I'm going to talk about today is cryptography for safe machine learning, and I'll explain what I mean by all this. So first thing I want to say is that, as Dean Curtis said, I graduated from Berkeley, and this was 1983, and I've been in this field for a very long time because also my PhD thesis was about sort of cryptography in a very early stage of cryptography. But having graduated that early and even attended the first crypto conference in '81 that was ever took place, I've been witness to a lot of consequences of very basic research and theoretical research in cryptography, like electronic commerce, which we all know about, cryptocurrencies these days, the ability to do cloud computing, somehow believing that your data and programs are safe, at least in transmission. The idea of a quantum computer that came up from Peter Shor, a theory computing researcher, trying to break a crypto algorithm, the RSA, on a quantum hypothetical computer at the time. So all this is to set the stage that I believe that today the kind of central question for cryptography is how can cryptography change machine learning, or rather not change it, but shed light on it and make it better. And I'm not a machine learning person, although at this point I've written some works on it from the cryptographic point of view. So I'm going to think of this extremely abstractly. There are lots of models, lots of application areas. I want to think of this as just as a magic algorithm hidden in some black box. So there's some black box, maybe what's written in it is a formula that takes some variables. These are the inputs, x1 comes in, x2, x3, and it gives you, it evaluates some logical formula, then tells you 0, 1. Maybe it is answering whether an email is a spam message, whether it's if it's, the input is an MRI image, is a tumor malignant, maybe it's an application to college, should the student be accepted, maybe it's a loan, should the loan be approved, maybe it's the profile of a suspect, and should he be released on bail? Very relevant to this proposition that just was denied in California, Proposition 25. We'll talk about that a little later. Anyway, so machine learning for me is something very abstract. It's a box. I give it an input and it outputs some 0, 1, telling me yes, no. It could also be, of course, more than 0, 1. It could be a probability of several events, not just one yes or no. But this is sort of the purest, simplest form. And in fact, if the theoretical world obviously would love to learn a C, but some analysis from a theory perspective, one of the sort of the earliest really, if you go past inductive inference, and you look at a complexity theory type definition is by Valiant in '84, where he publishes this paper, A Theory of the Learnable. And here's how he defines this box, or what we want to do really. What is our task? Please stop me. It's very weird. I'm kind of lecturing to myself. I only see myself on the right. So if there's some way that something very pressing, do ask me a question. Anyway, so back to Valiant, very abstractly, he says, say you're in a situation where you're given examples of this box. So you X inputs and then the verdict of the box, C of X. And let's say that X is drawn to according to some distribution. You may not know it. Let's call it D. And we say that a learning algorithm essentially is a parameterized thing. It has two parameters with it. What it's supposed to do is to efficiently generate a hypothesis H. So if you like to think of it as another box H, and what the requirement is that it will agree with C approximately and with high probability, as long as the inputs that H will see are also from the same distribution, D. So putting some math onto it, the probability that this hypothesis you came up with is different than what the box would say. We want the difference should be small, so less than epsilon, and we want that to be true with very high probability, greater than 1 minus delta. Okay, so this is 1984, and this is really actually the starting point. There's also a relationship between cryptography and machine learning, which is what my lecture is about. And my lecture is really going to be divided into two parts. The first part, I'm going to talk about historically how cryptography and machine learning interacted. And then the more interesting part is the second part, which is how it is interacting today. So at the time, if we're going back to 84, one of the kind of questions that complexity theorists ask always is, okay, you define what machine learning is or what pack learning is. Are there some concepts, some boxes C, which are not pack learnable? It's just an impossible task. And since I think Les Valiant was at Harvard and Rivest at MIT, it was kind of a natural question to be answered from a cryptographic perspective. And in fact, there's an early paper by Valiant and Kearns in '86, which they show that if cryptography exists, or specifically secure RSA encryption, if RSA is a secure encryption scheme, that implies that there are actually concepts that are even simple concepts, simple complexity-wise, so low level complexity classes, which are not pack learnable. In other words, the fact that cryptography is successful means that you could define a class of concepts, pretty simple box to evaluate, but still, if you just look at examples like X's in the answer of the box, you can't pack learn it. And since then, there's lots other results that extend this Valiant Kearns, where they change the model, like the person who's trying to learn might know something more about the box, might have some partial specification of it, and other type of restrictions. And yet you can show that there are even such boxes where you know a lot of information about it, you still can't learn them if certain kind of encryption schemes exist. So the upshot here is that Bliss for cryptography seems to be nightmare for machine learning. So the relationship was strong, but somewhat adversarial. And it wasn't just about classification, but even for generation. So another things that people do in machine learning these days is they say, okay, we have some distribution, let's say locked in a box. Now it's not the classifier, C. And it just outputs for you, you press a button and it outputs examples. So it could be examples, if people like to talk about examples of cats, of dogs, and you'd like to come up with another box which generates things that are indistinguishable from the real cats or indistinguishable from the real dogs. Or if you like, indistinguishable from pictures of one thing or another. And that's another kind of learning task. Also for that early on, like I think it was around 95, that it was shown that if digital signatures exist and other cryptographic primitives, you can, in a sense, define a box, which seems like a pretty efficient box, but if you just look at examples of it, you won't be able to mimic it. Hold on a second, I'm just gonna close the door here so it'll be quieter. Okay, so this went always in the direction so far that cryptography is showing machine learning people that there are things that they won't be able to do. And then in '83, something happened, which I don't think was paid attention to by a lot of people, but in retrospect, a very important result. So in Crypto 93, there was a paper by Lipton, Blum, a lot of other very central people in actually machine learning that said, you know, so far, essentially all hardness results, in intractability results in Valiant's model are based on some sort of cryptography construction. In this paper, we give results in the reverse direction. So we're going to show you how you can construct cryptography based on assumptions in learning theory. So before we said, let's assume RSA is hard, let's assume RSA is a good system, something in learning is hard. Let's assume there's good digital signatures, something in learning is hard. Now they say, you know what, we want to help you out. We want to give you good cryptography. But the way we are proposing to do that is that we're going to show you some problems we have not been able to solve in learning theory, but they're very different than RSA. They're not number theoretic. There's a very different type of problems. Maybe they would be good for you to construct digital signatures based on them, encryption, and so forth. And the specific problem that they mentioned in that paper is something called learning parity with noise. And the problem is this. Let's say that you have a secret vector, just of 0 1s. Okay, so it's an n-bit vector. And the learning parity with noise problem is, now someone gives you a bunch of equations in these unknowns. So S has unknowns S1 through Sn. These are all 0 1 unknowns. And I'm not going to tell you what the SIs are, but I'm going to give you a bunch of constraints on them, some equations. It's all mod 2. So I'm saying if you multiply 0 by S1, 1 by S2, and so forth, then you're going to get a value, all mod 2. The thing is, obviously, if you took linear algebra, if you actually will give me all these equations with enough constraints, I will be able to find S1 through Sn, just doing some sort of Gaussian elimination. So this is where the noise comes in. I'm not really going to give you these solutions, to the right-hand side solutions. I'm going to give you noisy solutions. So sometimes I'll flip the 0 to a 1. Sometimes I'll flip the 1 to a 0, depending on the outcome of some coin toss. Okay, and there is some noise, so the coin toss is biased in a certain way. And it turns out that even for small noise, this becomes a very hard problem. It's a machine learning problem. It doesn't look like RSA. It doesn't look like has no factoring in it. There's no discrete log in it. There's no hard number theory problem in it. It comes from a different source. However, what's interesting about it, it's the best running time is exponential to, in n, 2 to the order n over log n, I think is the best. It's still from 2003. It has some nice other properties. You can do some worst case to average reduction. So it's not just hard for some equations and for some S, but it's sort of hard for an average equations in S. And but the most interesting part, so then cryptographers listened to it. I think there was some systems proposed, but they didn't go very far. The interesting development happened in 2005 when Oded Regev, who's now in NYU at the time, I think he was at Tel Aviv University, said, you know what, let's take this LPN and make it into a new problem. We're going to call it the learning with error problems rather than learning with noise. What's the difference? So now his variables S1 through Sn, they're not binary. They're not just 0, 1. They're actually in ZQ, which means sort of if Q is a prime, they kind of go from between Q and minus Q. Actually, Q over 2 and minus Q over 2, it doesn't really matter. So they're larger numbers. And you're still not told what they are. That's the secret. You are still given equations. Now the equations are not just the coefficients are not just 0, 1, but they're also mod P. They're also in ZQ. And if all the computation is done mod Q, so here Q is 17. Now on the right-hand side, now it's not going to be just 0 and 1. It will be elements in ZQ. So he says the way that I'm going to put noise in, it's not going to flip. I'm just going to add some Gaussian noise. Okay, so it's a different noise model. Obviously, LPN is a special case, so this can only be harder. It turned out that not only that it's harder, but it's like a gold mine. So what has been shown by Regev at the time, that it's actually equivalent to a kind of a fundamental, well-known geometry problem, which I'm not going to dwell into it, but it's called shortest vector, computing the shortest vector in a worst case integer lattice, in fact, approximating the size of it. For this, you can have a very high noise level. You have a very nice worst case to average reduction. Still, it's as hard. Best known algorithm is exponential. But the most interesting part is that this problem has been revolutionary for cryptography because we were able now to build encryption schemes and digital signatures and many other things which have extra properties than what they had before. In particular, I think the most well-known and probably the most fundamental primitive that has been people were able to build based on the hardness of this problem is homomorphic encryption. which is a way to encrypt so that you can actually do computations on ciphertext on the encrypted version of data without decrypting. And do computation means you can run arbitrary programs on encrypted data and get the encryption of the result. So that's kind of incredible that, you know, the encryption, even though it looks opaque, has structure. Moreover than that, this has also a big quantum significance. So I mentioned quantum kind of in my first slide, just a short, you know, dive in for 1/2 a minute. So, you know, quantum computers was sort of a figment of Richard Feynman's imagination, really, who envisioned that someday maybe there will be a powerful one, but it was on paper. And in 1984, Peter Shor was then in Bell Labs, and I was at MIT. He invented a fast factoring algorithm that runs on this hypothetical quantum computer. I think the best, no, maybe now it's bigger. There's a bigger than 143. I think it's, I have it in another slide, sorry. The biggest number that can be factored by a real quantum computer, but it's still something like, maybe it's a 6-digit number or something like that, which is not a big achievement. And it's a single number. It's not that they can always do that. And in any case, even though that's the case, since around 2016, there's been a major race between companies, between governments. I think it was an announcement of by the Chinese government of a project that has set everybody off to try to build a quantum computer that can deal with large numbers, let's say ultimately, can do things that classically we can't do and much faster. So much so that I think in 2017, the National Institute of Standards and NSA called for saying, listen, we can't use the kind of cryptography we're using these days based on number theory. We need to think about post-quantum cryptography, namely cryptography, which will be resilient even when such a quantum computer will be built. Might be 10 years, might be 20 years, might be 30, but we have to start preparing to change our entire infrastructure so that we are ready for such a moment. And the reason that I'm dwelling on this is because it turns out that we are sort of prepared. And the reason we are prepared is because of that learning with error problem, which was a generalization of the learning LPN, learning parity with noise, was suggested in that 93 paper. Almost not the story, I'm changing a little bit for my sake, because what happened was in 96, Miklos Aitai from IBM showed the possibility of cryptography using geometry. And then Regev showed that this learning with errors is essentially, we can think of it as this geometry-based cryptography. So he showed an equivalence to it. And the point is that since then, since that era of 96 on, we have been able to use this geometry-based cryptography rather than the number theory. And then when Regev came out with his learning with error interpretation, it became even more easy to use. And we have a host of cryptography, all not breakable by quantum computer. And in my mind, all very inspired by this connection to machine learning. Okay, so this is a long story, but you know, a distinguished lecturer, I can say whatever, I can take whatever routes I want, and you are learning something probably. But coming back to our origin slide, where I said that I think cryptography is going to be important for machine learning. At this point in the story, it seems like all we've shown is that the bliss for cryptography is a nightmare for machine learning. And that's kind of a downer message. So this is where my talk goes into its second phase, where I want to say that in the second part of the talk, impossibility results actually for cryptography. So sorry, good cryptography. So homomorphic encryption, a difficult to break cryptography like quantum computers, cryptography that's agile, that can do homomorphic operations on encryption on ciphertext or data, are actually going to be positive news for machine learning. So I think I could take a breather here and ask if any questions on the first part of the talk. Is there anything in the chat? No?
Anyone have any questions?
Otherwise I can just continue.
I guess so.
Continue. Okay. So basically, the second part is really where I'm going to start talking about safe machine learning. So the thesis of this talk is that there's a lot of cryptographic tools, models, perspective from the last 30 years whose purpose was not just to do safe communication, so sending messages which are encrypted or authentic, but actually we've been doing a lot of work on privacy and correctness of computation. So I don't know if you can see my cursor, but rather than just communication. And all this work, I think, has the ability to ensure that the power of machine learning algorithms is not abused. So what do I mean? So this is what I mean by safe machine learning. It's not a definition. So the way I'd like to argue what it is, I would like to talk about some problems that machine learning is facing and how cryptography can help. And I'm going to do that just by going problem by problem and also describing my work in the field in the process. So I guess the first problem I want to talk about is actually not to do with privacy, but it has to do with verifiability. So correctness, a verifiability of machine learning models. So here's a question, which is not a privacy question, but it's how do we make sure? So somebody gives us a machine learning system. They say it's a great system, you should use it. So for example, in the context of California Proposition 25, it might be a system that tells you whether to let someone out on bail or not. You know, Proposition 25 was about eliminating a cash bail and using algorithms specifically to decide whether, you know, to give bail or not based on some kind of a historical database. And of course, I mean, I don't know if you know, but it was voted down. So it's not going to take place. But a major question here is, suppose that there is a machine learning that has been adopted by some for purposes of bail or purposes of giving you a loan and so forth, and some company came up with it. How do you actually ensure that it's accurate? So they're giving you a program, and now from now on you're going to use it. One thing is to say the program doesn't have bugs in it, so it's not going to, you know, bomb in the middle or something like that. But another thing to say is actually, how do I know that it's accurate? Now, accuracy is one concern. You could have concerns about fairness. You could, with respect to minority groups, you could have a lot of concerns. But I'm talking about even just about the basic accuracy. So we want to make sure of that at least with respect to a given distribution, it's accurate and there hasn't been any bias introduced for profit, for making your life easy, for control, for whatever. So one of the goals I think that we should have in front of us is to develop methods to verify efficiently that models are accurate for a given distribution. What do I mean with distribution in context of bail, for example? So it might be historical data, it might be new data, the distribution is induced by this data set. Of course, this is not the only question that is that should be on people's mind when they worry about verification. And it's not only from the point of view of how you don't have to think of it as a verification question. This is how I think of it, because I think of it through a cryptography lens, and that's what I'll talk about. But of course, in optimization, people have been talking about minimizing the effect of bad inputs. You know, in system security, you want to come up with secure infrastructure where you can run the model so nobody can tamper with. But I'm going to think of it from this point of view. We have on one side a box, which is the machine learning company or algorithm, and it's the red box, and on the other side is whoever's going to be using it. So it's a verifier. I'm going to think of this guy as a learner that then has to prove something about his algorithm to a verifier. And the ground it's not exactly the ground truth, but the thing that I have to work with is a distribution over, it could be a distribution from the past about people who were up for bail and whether you gave them bail or not, whether if you didn't give them bail, did they really recidivate? Did they commit a crime or not commit a crime when they were out on bail? This is what you have access to, okay? Now, what the learner does is let's say, uses this distribution and comes up with a machine learning model. And I'd like to think of this interaction as if he ships off the machine learning model to the verifier. He said, here's my program. This is what I claim you should be using for the future to classify whether someone should go out on bail or not, or in general to use as your hypothesis for the model of the concept that it was locked in a box. Now here's my hypothesis, take it. And the verifier wants to check that this is in fact consistent with, this is what he should be doing. They go back and forth, and at the end he says, I accept your hypothesis or I reject it. Okay, so what's the question here in this model? My question is, look, the prover may want to give you the algorithm, but he might have taken a long time to come up with it. The verifier doesn't want to redo all of the work. He wants to be able to quickly verify that this algorithm that he was given is accurate. And maybe you should think of this, and the way we think about it is that the algorithm is a black box. So I'm not looking at it inside. All I can do is give it inputs and get outputs. This is a joint work with Jonathan Shafer, a student at Berkeley, Guy Rothblum from Weizmann, and Yehudayoff from Technion. And it's going to be an ITCS coming up. Now, what is the difference between the learner and the verifier? I'm going to say that the verifier in some sense is weaker than the prover. Weaker how? Maybe computationally weaker, but more importantly, he's weaker in his access to the data, to the distribution. It may take lots of samples. Maybe he can even ask queries from the data. So give where the verifier maybe just gets fewer samples, maybe just some random samples. And I want to show cases, or in general, a whole theory where this is sufficient for the verifier to verify complicated claims. So what we do in this work, we come up with a new concept, so a formal concept called pack verification. I don't know if the audience is composed of people who are more theory-minded or not. This is a formal definition, but I'll just kind of talk through it. So remember that we had pack learning. There you were getting examples and you were supposed to come up with an hypothesis. We'll say that a given hypothesis is pack verifiable, okay? If there exists a verifier and a prover, you think about those red and green boxes on the previous slide, such that the following is true. I want to have the case, I want to define something that's just called a loss function. What's a loss function? It's the difference between what this hypothesis says on X, okay, then what the true answer is, okay? I want to think about the optimal, okay, so opt to be essentially among all possible hypotheses in a certain class, how much do you lose? So could be the black box is some very complicated thing. You came up with an hypothesis from a certain hypothesis class. And I want to know what's the best you can do. And that's the optimal. So that's the minimum amount of loss that this company could incur if it did its job properly. And to verify, I'm saying a verifier checks this if he satisfies both completeness and soundness. So what is completeness? Is in fact, there is a procedure, a prover, that will convince the verifier to accept hypothesis, but that's only going to happen when the loss is small. That indeed, the thing that I'm being handed off as a verifier, it obtains small loss. So I'm close to the optimal with high probability. And soundness, which means that if, in fact, the learning algorithm is not close to the optimal, then it doesn't matter what the prover is going to do. No matter what tricks he has up his sleeve, the probability the verifier will accept is low. So in other words, I want to make sure that if we go into the previous picture, this guy is going to accept good hypotheses, good meaning they're close to the best that can be done, and reject, or as close as what's being claimed by epsilon to what can be done, and reject otherwise. And I want this all to be efficient. And when I call this double efficient, which is I don't want it to be much more expensive for the learner to convince the verifier, and I want it to be efficient for the verifier. Okay? And this is sort of a subtlety, but it's sort of, there's something called an agnostic case and not an agnostic. So it's what I'm trying to verify is this formula, that the loss is close to optimal. So loss minus optimal is less than epsilon. So there's sort of two things that the verifier needs to check. First of all, what's the loss of what you received? And second of all, how far it is from an optimal. And it's not so hard to estimate what's the loss of what you get. You just sample at random and see if it agrees with what your sample, what the hypothesis says. But it's hard to estimate what the best would have been. And that's what the prover needs to convince the verifier. So we have positive and negative results. This is a model. I think it's more interesting actually to think about the model, to think if it's the right model or not. But given this particular model, we have some, essentially positive and negative results. So for example, here's a positive one, which is a whole class of type of functions. These are functions which I call T-sparse, some mathematical definition in the Fourier space, but it's a large class of signals, of functions. And what's interesting about it is that to learn it, you actually need, it's not enough just to get random samples from the distribution. You need to ask what we call membership queries. So you need to ask questions, give X and get back Y, or if you think about the box, give X and get back the label. But we showed that to verify it, in contrast to learning, the prover still has to learn it with membership access. But to verify random access samples, so you can't just ask X of your choice. You just get a bunch of random samples of, let's say, feature vector of what the accused profile is and whether they were let out on bail or not in the previous system. And given this small random sample, you now would like to be able to verify whether this thing that the learner shipped to you, this box, in fact is accurate as it claims. Okay, so this was one task. How do we verify the accuracy of a machine learning model? It doesn't dive into the details of the model. It could be a neural net, it could be a linear regression, it could be something else. All I know is that somebody's handing me a box and I want to be able to verify it, not using too many samples and not using sophisticated access into the distribution. By the way, there's other things you might be able to verify. You might be able to verify, this is a project that we're working on now, whether the algorithm obeys fairness for some definition of fairness. How do you verify that? One thing is to actually make your algorithm fair. Another thing is for me to verify that your algorithm is fair. Okay, let's go to another challenge. The next challenge I want to talk about is robustness. What do I mean by robustness? So a big topic in machine learning that people have been talking about for a long time, at least long time in our life is, whatever, in a month, it's amazing. So we're talking a few years, maybe 3 years, is adversarial machine learning. So what's adversarial machine learning? Clever manipulations of inputs. So let's say we already have an hypothesis and somebody now wants to kind of defeat it. So let's say it's a self-driving car and it learns to recognize signs like stop and yield and so forth. And somebody wants to cause havoc. So they try to manipulate the sign, let's say the stop sign, so that it looks like to the machine learning algorithm like an yield sign. The goal is to cause misclassification and full applications. So big question is, how do you make your machine learning algorithm robust against such possible adversarial behavior? And if we want to think of a picture, let's think of it this way. The adversary, the one who wants to manipulate, let's say, the stop sign, he might have access to your algorithm. So it sees how it works. Maybe it sees the inside of it. Maybe it just has black box access. And there's lots of examples out there where it's amazing what an adversary can do, how he can cause a misclassification of natural images and have the algorithm completely label it incorrectly with respect to how a human would label it, for example. The thing is that when you want to kind of make your algorithm robust to input manipulations, you have to think about who is this adversary that's manipulating your input. And currently in the literature, in the machine learning literature, what is done is you define a class of sort of domain-specific attacks. So in the case of vision, it might be rotation of a picture, changing some pixels, things of that sort. And then you prove that your machine learning algorithm is robust to such attacks, maybe by actually training it against such attack, to be robust against such attack. That's the current dogma as far as I know, and it seems reasonable. However, if you think as a cryptographer, we never think this way. The whole premise is the adversary's worst case. I have no idea how he's going to try to break my system. I have to be prepared for the worst. And I am going to prove that regardless of what the adversary does, it's not going to break the system. So usually our proofs are kind of reductions. We say, let's take an adversary. I have no idea how it works, and I'll show it can't exist by converting it to something that, let's say, factors integers or breaks learning parity with noise or some other problem which cannot be broken on any classical computer or any quantum computer in the future. So a cryptographer's view of what's happening in adversarial machine learning is that it's not enough. That we would like to consider worst case adversary, someone who can do manipulation of the input in any possible way, maybe limited to polynomial time that we're willing to talk about, but I can't restrict the strategy. And this is the subject of another paper that I have with Adam Kalai, and I wrote Adam, but it's Adam Kalai, Yael Kalai, and Omar Muntasar from TTI. It's going to appear in Europe soon. And we call this beyond perturbations, learning guarantees with arbitrary test examples. So this is arbitrary. The adversary could be anybody. In fact, it's not even restricted to time. So I'll tell you a little bit about this. This will be that's the next one. The idea is, how do you make learning algorithm robust for any adversarial test distribution, with an emphasis on when it's possible. So let's look at an example. Very simple example, not so complicated. So let's say I just wanted to learn a half space. So these are plus training examples, these are minus training examples, and I want to find out what is a hyperplane that would separate pluses from minuses. So this is a natural example, guess, right? It certainly separates everything I've seen. And in fact, now, what does that mean? It means that when a dot comes, so that's a new test example, and this is my hypothesis, this is my classifier, my H, or I call it F hat here. If you give me black dots over here, it will say plus. If you give me black dots over here, it will say minus. And that's completely, this would be pack learnable, according to the pack learning definition, because the training distribution, which is these minuses and plus, the reds and greens, is essentially the same here as the test distribution. So the dots are coming with, close to where my training examples were. But an adversarial situation is that the distribution of training and the distribution of testing exactly is not going to be possible. So what my adversary is going to do, he's going to try to come up with dots which actually elude this F hat guy, this hypothesis that I came up with. So for example, what could he do? He could give me dots over here. Or he could give me, so if you look at it, if this was the true classifier, okay, it still would be okay with respect to the pluses and minuses, but it would be incorrect with respect to these, because here, these guys should be pluses, these guys should be minuses, but this classifier would make them all into minuses, and similarly the other way. So it's very easy to come up with examples where as soon as what you're being tested on is different distribution than what you saw in training time, all bets are off. You cannot come up with an hypothesis. It's not a question of being clever. You just cannot come with an hypothesis that's not going to make a lot of errors. So what do we do? So we relax the model. So why is this cryptographic? Well, why did I say that the cryptography is helping out here? One is because we're considering worst-case adversaries. Two is, it's been a tradition in cryptography, I think, really from 1976, when Diffie and Hellman came up with public key cryptography model, is that the model is everything in some sense. You can't do it, let's say information theoretically, let's restrict the adversary to be polynomial, or come up with a model which is meaningful, which is useful, and which you can achieve. And we're going to do the same here. So the first relaxation is going to be that we're going to allow the learner to either say, let's say in that example of the half spaces, he can say plus, he can say minus, but he can also say, I don't know, I abstain. Okay, so he's allowed to give a question mark. Now, this is not a new idea. It's been considered in the context of cryptography, going back to 57 actually, and then Rivest and Sloan in 88. But when they did that, they were saying is that they allowed abstain, but they didn't think about an adversarial setting. So it was just a distributional setting where you were getting a distribution which was different from the training distribution. And in any case, the answer are kind of negative in the sense that you cannot get good labeling and abstaining. So in other words, you can't do well in just relaxing the model to allow abstain, where well would be the natural well, where you would essentially classify and do abstaining. And when you do classify in plus and minus, you are you're doing it with good parameters of success. So I mean, there's some examples to look at, but I think it's too much in the weeds to get into. We have a new notion. So what we are proposing is a new notion which we call PQ learning, and that is where, let's say the training distribution was P, and the test distribution is Q. Okay, so this is what we saw when we were training, but this is really what's coming in. And we are going to allow the learner to abstain, but we're going to allow one more thing. That's how this model is different from just letting the answer to be yes, no, abstain. We're going to give the learner, in addition to the examples from in the training time, labeled examples like an example of a plus, an example of a minus. I'm also going to give him an example of a bunch of X's without labels from the test distribution. So notice here, what is this giving me? It's telling me that the test is telling me something about, it doesn't tell me whether these guys are pluses and minuses. It just tells me what the test distribution is, examples of the test distribution, and it gives me an opportunity to be able to look at the differences between these two distributions. What do we require for successful PQ learning? We require that there is on one hand low rejection on P. So in other words, when you have a test distribution which is actually the same, let's say. So actually you were tested on what you were trained. You're not allowed to use, you're not allowed to abstain. That would be unfair, okay? Because then you could just abstain all the time, right? There you have to essentially abstain with very low probability. And we want you to be correct, so low error on a different distribution. And what we're asking is, what can you prove on the sum of the rejection rate and the error rate? So of course we want this to be low. So we want you not to reject when it's something that you should be able to answer. And we want you not to err on something that you haven't seen before. And you don't have a chance to really always classify. In other words, you could reject on Q. You could say, I don't know. But when you don't say, I don't know, you got to be right with good probability. And what we are shown is actually that we can do this. So it's sort of a reduction from, regret minimization. So if you have machine learning in a sense that in a way that can be done now, then you could do it. And we get this bound of square root of the VC dimension over N. It's tight. Okay, I'm done with my robustness example, and I want to go, I have a few more minutes, I think, before Q&A, right?
Correct.
Okay, so now I want to go to privacy. Usually I would have started with privacy, but privacy is sort of the first thing that comes to mind. And in fact, a lot of people have done work on it. So what is the privacy question? We know that a lot of the strength, or basically, maybe this is going to change, but today the strength of machine learning is because we have so much data. And this data is our data. But these days it's being held by third parties because it's collected on us, or even if it's not being held by third parties, it's very rare that a company, not Google, has enough computing power to run big machine learning models. So they have to go to the cloud and use cloud services. No matter how you look at it, our data is out of our hands. And it means that in some very strong sense, power is out of our hands. So privacy really is, if you want to think about it this way, it's a way to, if you keep your data private and somehow enable the cloud to work on it, or and get utility out of it, then you are retaining power to some extent at least. And when we talk about privacy of data in the context of machine learning, we talk about training data, training inputs. Maybe even when you want to classify, you don't want the cloud to know what is really you're interested in which picture you want to classify. You just want to use the power of classification. There are lots of works on it. It started with feasibility type works, then asymptotic efficiency. These days, a lot of proof of concepts. The thing that it hasn't been done yet is really the challenge of training at scale. So if we think about it, there are many papers out there, should have really a long list of references here. I apologize that I didn't do that. Because but no matter how you look at them, they're not looking at the size of training that really matters for applications. So in particular, I am interested in data-driven applications in healthcare and drug development, where you really need large data sets and you need some data fusing, collaboration, let's say between many hospitals, many genomic centers. Say if you want genomic data, not every center on its own doesn't have enough data, but you need to collaborate if you want to have enough data. There's a lot of benefit, obviously, from doing it. And yet, privacy is a problem. So the next work I want to talk about is actually work on this problem, and it's done with people from Duality, which is actually a company that I co-founded. We're looking at GWAS, a genome-wide association study. So I'm sure you all know what it is. It's essentially an observational study over a large number of individuals, which is able to associate genetic variations like genotype with phenotype, like real traits and diseases. And how are these genetic variations represented? It's something called a SNP, or single nucleotide. Each genotype includes roughly, the reason I'm putting all this here, because I want you to get a feeling of the sizes, like 500,000 to 5 million SNP. And the way the GWAS works, it evaluates one at a time for association with a phenotype. And typically performs things, statistical tests like logistic regression, goodness of fit test, and then talks about what your errors are, p-values, and so forth. So it's labor intensive. And now we're talking about doing this with lots of patients, and each patient having a genotype, and we want to add privacy to it. So just before I go to the privacy aspect, I want to say that these days people have, going from GWAS to talking about polygenic scores, where we give people a score for what is the chance you're going to have a common disease, let's say. What is your risk? And so you sort of give a score, or if you think about it, you take a linear sum of what genetic variation you have times what the weight of it is, you do a sum, and then you get your own risk for disease. And this is actually very interesting. It's really seems to be very timely, and people are working on it more and more. And it's particularly timely even in the context of, let's say, COVID, because people want to know who's going to get COVID in a serious fashion, who's not. And there's organizations that are storing genomic data that want to identify what variant makes you especially susceptible and especially have a bad response to COVID-19. The idea is that you're going to have like a database of people who've had COVID, people who haven't, what kind of symptoms they've had, and so forth. So and there's a hope to understand who's at risk. So in any case, the barrier here to all this wonderful work is privacy. So it's actually, especially genetic privacy. We know that it's identifying personal genomes. You can find out things like eye color, family relationships, many things just because from your genetic information, and sometimes some extra information that's left behind associated in the metadata. So still, this is, we relax. We say, as cryptographers, this is our playground. We know how to do privacy and functionality at the same time. We will be able to run GWAS and keep completely private the genetic information. And it's true. The stuff that we have developed in the last 30 years, things called garbled circuits, homomorphic encryption, multi-party computation, secret sharing. There's all these tools out there that are exactly defined to address this problem. How to run GWAS on completely encrypted data? Yes and no. What's the no? The no is that, sorry, I want to skip this slide, that there's a big barrier, and that's scalability. So these, our cryptographic machineries, once you put them to test in real applications, they have to deal with large amounts of data. And in particular in the area of genetic analysis. So I think this was first shown in the context of schizophrenia, where they saw that when they went from 3,500 cases, this is a slide by Manolis from MIT, to 35,000 cases, all of a sudden, whereas before they didn't see any genetic relationship to schizophrenia, all this stuff came out. These reds are places in the genome that are associated with schizophrenia. And it's not just true for schizophrenia, it's true for Crohn's disease, for breast cancer. There's all these charts out there which tell you that this is in thousands, the number of patients, the difference between 200,000, 400,000, about how well you can do, okay? once you get big numbers. So to do training on encrypted data means that we should be able to somehow use our cryptographic machinery on large scale data. So a paper on this appeared in Science and then Natural Biotechnology. I think the first paper is a group from Stanford, et al., and then there's a paper in group at MIT by Berger et al. And what they said is, let's use something called multi-party computation. And here's the idea. And the idea is, just 1 second, I will lower some noise. So the model here is the following. The study participants, let's say participating in the GWAS, okay? These are different hospitals or different genomic centers. And what they're going to do is they want to do GWAS together on collaborative data, but they don't want to tell each other the data. So what they're going to do is they're going to sort of break their data using something called secret sharing, and then send the shares of their data to computing parties. So here there's 1, 2, and 3, or 0, 1, 2. This is in the paper from Bonnet. I think this is or maybe it's the Berger paper. It's the Berger paper. And then those 3 parties are going to do what's called a multi-party protocol. They send messages back to each other based on the data, and at the end they get the result of GWAS. Without any single party here did not see the data of any individual. But the underlying assumption here is that when you are sending it to these 3 servers who are working together to run the GWAS, they are trusted not to collaborate. So it's kind of a weird model where you are giving data to servers, outside servers, trusting that they're not actually going to try. There's no one there who's trying to find out and reconstruct your data. So this is the model that they use. And what they showed was that for age-related macular degeneration, with 21,000 individuals and 220,000 SNPs, that they can run some tests, which are typical for GWAS tests, and identify the most significant SNPs that are related with AMD, with this disease. They extrapolated from what they did that they could go to many more individuals, like 100,000, 500,000 SNPs, and then the runtime would be something like 193 hours, which is not bad. Logistic regression, on the other hand, was prohibitively expensive. They couldn't actually run logistic regression using these 3 parties collaborating, and for the numbers that they ran it on. So the natural question for me was, what about homomorphic encryption, which is another type of technology in cryptography, the one that I've mentioned before, based on sort of this learning with errors. But they wrote in the paper a very strong prediction. Homomorphic encryption will take many years of computing, or petabytes of communication at the scale of 1 million genomes, and therefore not viable. And then the other paper, same things. So what I'm happy to report is that we actually dispel this. So we, in a paper that appeared in PNAS recently, we use a different technology, crypto technology, where the study participants, like the hospitals or genomic centers, encrypt using homomorphic encryption. And then you just compute on the encrypted without decrypting them and send the result back out. And they're encrypted. And then to decrypt it, the study participants can go through a very simple protocol to remove their locks from the result. And what we get in terms of is that we can do logistic regression, which was previously even infeasible for small numbers, and the chi-square test, which is similar to what they did on the same data set. And in terms of our extrapolation, it would be like for chi-square test, a few hours and 6 hours, and for logistic regression, 234 hours. So if you look at it as a slide, and we are going to individuals, going in the 100,000s, and sorry, here individuals, and something here is wrong. This one is SNPs. Something in my yeah, I think this is in terms of SNPs, and this is in terms of number of individuals. So this is good news, and it's good news for homomorphic encryption beyond GWAS. More generally, there are packages out now which are open source, HElib, Palisade, Seal from Microsoft, and so forth, which I believe I can sort of safely say that if you have the right data scientists working together with cryptographers, you'll be able to solve problems much larger scale than you've believed before. Okay, almost 5 minutes. I'm just going to say that this is not, those three, verifiability, robustness, privacy are not the only concerns. There's compliance with regulations. As you know, there's GDPR, which talks about what data you're allowed to use and how to use it by big companies. That brings the obvious question is, how do you know that a company is complying with GDPR? One thing is to break, and another thing is just to test compliance. So that means that some kind of method to trace whether your data was used in an unauthorized fashion is a very interesting question. One work that I've been involved in with Prashant from Berkeley and Sanjam Garg from Berkeley was how to be compliant with one part of GDPR, which is that if somebody wants to remove their data, let's say from Google, like if there's a query to Google that shouldn't be answered. There was some case that was tested actually in Spain that a company like Google will have to do it. So it's called, our work is about what's called the right to be forgotten. So how to be compliant with an order that says you got to erase me from your system. How do you erase someone from a machine learning system? How do you erase their data? Not a trivial answer, and I think an interesting one. And then there's questions like, what kind of randomness should you use in the context of machine learning? How does it affect your accuracy? How is the randomness generated? Another question you could talk about is what cryptographic functionalities are sort of important for machine learning. Right now, we sort of do all the tricks of the trade, but maybe there's one thing that we should kind of focus on in terms of making it efficient and it would be important for machine learning. Or the reverse question is, maybe machine learning people should use as their basic functions things which are crypto friendly, so which are efficient to implement when your data is encrypted. So I think this is it. This is all I wanted to say, and I just plug in for Simon's. There's two programs that we still have going on for about another month and a half. One is on probability geometry and computation high dimension. The other one is theory reinforcement learning. You just go to the Simon's website and everything's open. Thank you. Back to you.
Wonderful. Thank you so much for that terrific lecture. And now we're going to go into the Q&A session. And everyone, if you could please type your questions into the Q&A box on the webinar, that would be terrific. And then I will read them to Dr. Goldwasser.
Okay. I stopped sharing my screen so we can sort of talk face to face.
Thank you.
Okay, so it's in the chat.
Oh, yes, we have one. Okay. There is this idea of semi-supervised learning, which is very similar to your second adversarial learning example. The input is labeled P, labeled examples P, and many, many unlabeled examples Q. People believe that it should be possible to learn by combining some classification with P and clustering with Q, but it seems hard to make it work. In what circumstances does your theorem say that this is possible? Does having Q ever actually help? Maybe with some additional assumptions.
Okay, let me just read this so that I. Yeah, so that's what I'm telling you, that having Q, or having some examples of Q, which are unlabeled, we can prove this theorem. So the theorem is an algorithm. There's actually some implementation in the papers as well. Is that the question? That you can achieve, this sort of low rejection on P and low error on Q. Now, I think the interesting question here, though, there is a question here, is where you're getting Q from. Why are you going to have examples of Q? So first, my answer to this is, first, as a theoretician, I don't know. I don't care. It's an assumption. But seriously speaking, I think that there's lots of settings where you can imagine that like an online offline stage where people give you a lot of examples and you do a pre-processing beforehand. Let's say if you think, I think the example that we talk about also in the work is YouTube videos. Suppose you want to classify YouTube video as pornography or hate video or something, and you don't want to display it, you usually will process it right before, and you're not going to put them on. And you might have a whole class of such, such examples. Another interesting question is how do you seduce people or induce people to give you their examples? That's an interesting question. How do you elicit them? Okay. And now another question here. Have you discussed the ideas of pack verifiability with machine learning practitioners? If yes, what has been their reaction? What are the main challenges to apply some of these ideas in practice? I haven't discussed it with them. It's a good, it's kind of hard to discuss anything these days, as you know. You can discuss things with people you know, much harder to discuss them with people you haven't worked with before. That's a very good suggestion. Now, asking what are the main challenges? I don't know that, we're now working on things that are much more related to applications. So rather than like the Fourier things that are sparse Fourier coefficients, like I said in the talk, things where you can think of what the machine learning does is solving an optimization problem. So how do you prove the result of an optimization or linear programming? And I don't know that it's, in my opinion, that it has chances, good chances. Now, then there's of success also in practice, but there's obviously a big difference between writing a paper and building a system. But I believe that when you have the right ideas, these things are doable. Okay, now there's another paper here. Another question, how can you convince the general public about the validity and reliability of M? Very good question, right? Very good question. So Prop 25 is kind of, to me, I would assume that the reason why it was declined was because people are afraid. So they say, well, we don't know what these machine learning algorithms are doing. That's why I think it's so important for us to come up with technical solutions which are easy to explain, right? Just let's roll fast forward maybe 2 years from now, 4 years from now, I don't know. And we have verification systems which are good systems. We have fairness definitions which we can convince are going to yield results which are better than what's been done before. And that we've been also honest on the data that's out there, that it was biased, and sort of explain to people that there's merit in replacing. We're not making them worse, I don't think. Hopefully we're making them better. I think it's a lot of talks. First of all, it's getting the right techniques, but then explaining what is the data in the past, how do we use our tools to find out how the data was biased in the past, how our future tools are only improving. Having said that, we had a workshop in Simon's about a year ago called Wrong at the Root. Maybe it's less than a year. And it was about racial bias and algorithms. And the whole conference was full of people who were not technology people, a lot of lawyers, a lot of activists, and also technical people. And they basically coming from a standpoint of a lot of disbelief. So they're saying they've been in the field long enough. They know that once something is adopted, it's an uphill battle to unadopt it. And they don't believe that we're done everything in our power to make sure that we're not introducing more bias. And since I come from technology or from theory, I'm always excited about the fact that we can do what we can do, but it's hard to argue with history. So I think that's a big challenge. So in other words, what did I say? My answer to your question is good question.
We have one more person who raised their hand in the participant section. I want to give Lujan a chance to ask the question.
Okay.
Lujan, if you want to unmute.
Hi, I think Lujan might have stepped away. I tried to hit unmute, but I think that might be it. Thank you, Dean Curtis.
Okay, thank you very much again for sharing your expertise with us, Dr. Goldwasser. Thank you everyone who attended the lecture, and have a great afternoon.
Thank you very much.
Yeah.